So, this is VLSI data conversion circuits lecture 6. Let me quickly summarize what we were discussing the last time around. Last time we saw that the first non-ideality of the sampling switch that you can think of is finite on resistance. So, when the switch is closed, it does not quite behave like an ideal short circuit. There is some resistance, and every physical resistor which is in thermal equilibrium with its surroundings has a noise source associated with it. The spectral density of the noise source turns out to be 4 kT times the value of the resistance, and when the sampling switch is closed, the actual voltage across the capacitor is not simply the input voltage which has been filtered by an RC network, but also the noise of the resistor which also undergoes filtering by the same RC network. And when we calculated the mean square value of this noise voltage across the capacitor, we said after a little bit of math that the mean value of the noise as we expect should be 0, and the mean square value of the noise is the number kT by C whole square. And quite surprisingly at first sight, it seems as if this mean square noise is independent of the resistor. It is surprising because the only noise is coming from the resistor. So, it is a little bit surprising that the mean square noise is independent of the resistor and only depends on the capacitor. After a little bit of thought, we saw that yes, it does make sense, because even though the noise source strength increases with increasing resistance, the bandwidth through which this noise is filtered has reduced. So, these are two opposing effects, and magically they seem to cancel out, resulting in a value which is independent of the resistance. Okay. Now, this is somewhat bad news, I must say, because now with our sampling circuit we have definitely picked up the signal that we want to sample. We have also picked up along with it a noise A which is 0 mean, B which has a mean square value of kT by C, and towards the end of last class we discussed that the samples of this noise from instant to instant of the sampled output are uncorrelated, and the reason being that by design one would choose this RC network to have a bandwidth which is much higher than the sampling rate, correct. If you want to capture the input signal accurately on the capacitor, then you must make sure that the resistance of the switch is sufficiently small that the voltage across the capacitor is not an attenuated version of the input. So, by design you would make the bandwidth of this RC filter much higher than the sampling rate, which means that the time constant R on times C would be much smaller than the sampling time, which basically means that any voltage which was sitting on the capacitor before you close the switch will get completely discharged in the next cycle. You understand? In other words, if the RC time constant is chosen to be much smaller than the sampling time, the capacitor does not remember the previous voltage to a sufficiently large degree. So, pretty much it has forgotten what was there in the previous sample, which is equivalent to saying that there is no correlation between the sampled noise in successive samples. If there is no correlation between successive samples, it means that that discrete time process is also a white process, okay, and in the discrete time spectrum that will correspond to a flat noise spectral density. Okay. Now, from this argument we saw that it is not simply enough to have an R on times C time constant which is sufficiently small. As we discussed the other day, there are many choices of R on and C which will result in the same time constant. So, we would like to understand if there is any rationale to a specific choice of the sampling capacitor, and the consideration of noise gives us that answer. If you choose the capacitor to be too small, what would happen? You will have a large variance for the sample noise. Okay. On the other hand, if you choose a small capacitor, I am sorry, what did I say? If I choose a large capacitor, the variance of the noise is small and vice versa. So, we know that after we sample the input on the capacitor, it is going to be quantized. This sampling completes the sampling in time or quantization of time. The next thing is to quantize amplitude, right. So, now once we have the sampled value, it is going to be quantized. So, how do you think I will choose this kT by C? Do you understand the question? So, let us say whatever voltage is sampled on the capacitor, at this point let us say I have an ideal quantizer following the capacitor. The step size of the ideal quantizer is known, because that is, I mean, that is what you wanted to design in the first place. Now, the question is, how will you choose the size of the capacitor? So, what you will do is you will make sure that the RMS quantization noise, I mean RMS thermal noise is smaller than the step size of the quantizer. The idea behind this argument is that anyway you are going to lose some information after you quantize levels, you got to make sure that the noise that you add due to sampling is smaller than the step size that you use for quantization, all right. And therefore, pardon? Well, there is the question he asked was, why do I want to make this choice, right. So, what if the RMS quantization noise, I am sorry, the RMS thermal noise is greater than the quantization noise? What comments do we have? Well, let us say for argument's sake that the RMS thermal noise is say twice the step size of the quantizer, which follows. So,
output of that quantizer will not be correct as compared to.
that is true in either case, right. Whether the whether the quantization noise is smaller than thermal noise or not, we must accept that there is going to be an error between the input and the sampled output. Whatever we do, we cannot avoid that error, correct. Now, what we are arguing about is to see if it makes sense to make the thermal noise smaller than the step size or larger.
Thermal noise is closer, I mean maximum thermal noise is equal to the step size. You won't be losing a bit information. The resolution will not be degraded. Effective resolution.
Okay, so let me rephrase this question. So, what mistake am I making if I say thermal noise is maybe 3 step sizes? The RMS thermal noise is 3 times the quantization step. What argument do you have to say that? I mean, from what you are saying, it appears as if it is a bad choice, correct? Okay, the question is, why is it a bad choice? I agree that there will be, more error and so on, but
the possibility that it will enter go into the next step, it will be more.
Yes.
The lesser the thermal noise, the less chances of going into it.
Yes. Okay. So, the argument can be rephrased in this way. So, if the RMS thermal noise is much larger than the quantization step, then I can say that I am not as far as the whole process is concerned, there is not much lost if I increase the quantization step, isn't it? Because I am adding so much error upfront that it does not make sense for me to quantize so fine anymore, because I have already added so much error in the first place. Okay. So, I can use a quantizer with a much coarser step without really affecting the entire system. You understand? Does it make sense? There are two errors which you are adding. One is the KT by C noise that you add when you sample, and two, the quantization noise due to the quantization that follows. Okay. Now, the question is, why should I choose one to be much smaller than the other? So, if I chose the thermal noise to be larger than my quantization step, then somebody could argue that why do I then need to spend such a lot of effort in trying to build a quantizer with a small step? Presumably, it is much easier to build a quantizer with a large quantization step than with a small quantization step. Does this make sense? Right. So, if you want to resolve to a much more accurate value, it means that the quantization step has to be very small, but if you take the argument that I am going to have so much thermal noise right up front, okay, that its RMS value is much larger than my quantization step size, then as a quantizer designer I would say, hey, then why waste time and effort trying to design a very fine quantizer? Anyway, you have made such a big error up front. So, I will make my job easy and make a quantizer with a much smaller step size, a much larger step size, correct? You understand? So, if you want a final resolution for the entire converter, for the entire signal path, both sampling in time as well as in amplitude, then you got to make sure that the error you pick up finally from end to end is bounded, right, by some value. What we assume is that the sampling process results in a much smaller error than the quantization process. So, then you can say that the entire resolution of my chain is simply that of the quantizer. Is that clear? Okay. Yes. Well, yeah. So, now the question of whether we should consider RMS or whether we consider peak to peak is an open question, right. But some measure of the thermal noise must be smaller than the step size. Okay. Yeah, much smaller than step size. And again, now the question is, what is much smaller, right? A common value to choose is maybe a quarter of the step size of the quantizer. You understand? So, all right. Okay. Now, what implication does this have on design as far as high resolution A to D conversion is concerned? So, if you have a limited signal swing and if you want to resolve this signal to a very fine value, in other words the resolution of your entire A to D conversion process is high, then it must follow that the capacitance that you use for sampling is sufficiently large, so that the RMS thermal noise introduced due to sampling becomes a small fraction of the step size. The step size, you recall, is now much smaller because you are targeting a very high resolution. You understand? So, if for example the peak signal amplitude is A, then one can quantify the signal to noise ratio after the sample and hold as the ratio of the signal power to the noise power. The signal power for a sinusoidal input will be how much? A square by 2, the noise power is kT by C. So, the signal to noise ratio after sampling is A square times C by 2 kT, and this better be much larger than the required signal to noise ratio of the whole chain, which consists of the sampling operation plus the quantization operation. Does it make sense? Okay. So, the next thing to do is to try and figure out how one might be able to realize this using devices that we know. And as you are all aware, the MOSFET is an ideal candidate for this kind of work. We know from earlier courses that a MOS transistor, so the MOS transistor is an ideal candidate for use as a switch. Let me quickly refresh your memory. An NMOS transistor shown here has 3 terminals: the drain, the gate and the source, and the body. The body is usually not accessible in many technologies and is condemned to be connected to ground. So, typically as I was mentioning, the body is connected to ground and one has no access to the body as such. Technologies where this is possible for the NMOS transistors are what are called N-well CMOS processes, and what region do you think you would want to operate the transistor in if you want to make it behave like a switch? You want to operate the transistor in the triode or linear region when you want to make a closed switch, and you want it to be off when you want to make an open switch. And let me quickly put down expressions for the resistance of the switch, etc., when it is operating as a closed switch. So, what are the limits for triode operation? You got to make sure that VGS is greater than VT, all right, and VDS is less than or equal to VGS minus VT, and the threshold voltage itself is not really a constant, it depends on the source to substrate bias, and Vt is therefore given by some relationship of the form Vt naught plus some gamma times square root of Vsb plus 2 phi naught minus square root of 2 phi naught. All this comes from the theory of MOS transistors and is not, we will not go into these details, but as far as designing a sample and hold is concerned, we need to know these expressions. And in the triode region, the current in the MOSFET is given by mu n C aux W by L times VGS minus VT times VDS minus alpha VDS square by 2, where all terms have their usual meanings, and this alpha accounts for the variation of the threshold of the transistor along the channel length, okay, and is typically about 1.1 or 1.2. In most cases that we will deal with, we will be operating with such a small VGS across the switch, with such a small VDS across the switch, that one can actually neglect this term, in which case the resistance of the switch is approximately given by 1 by mu n C ox W by L times VGS minus VT. Pardon? Yes. No, actually the comment made was normally we see half VDS square in the equations, and where is alpha coming from? It turns out that half VDS square is not entirely correct, right. There is a the correct equation is to have, those of you who taken done a MOS modeling class or device modeling class will know this, that the standard way of deriving the I from the VGS and VDS is to assume that the channel charge is of the form VGS minus VT, right, and that VT is assumed to be independent of the location along the channel. In practice it turns out, I mean physically you can see that as you go along from the source to the drain, the depletion region must actually, the depletion region thickness must actually increase, because the source substrate potential is smaller than the drain substrate potential. So, the threshold actually increases as you keep going from the source to drain. So, and that this alpha models that effect. Anyway, do not worry about it if you have not taken a MOS class, all right, and you must bear in mind that Vt is a function of the source substrate bias voltage through the body effect. Okay. So, now let us come to our first version of the sample and hold circuit. All that we have done is replaced the switch with something which opens and closes based on electronic control, and that is the gate potential. Further, we assume that the whole circuit and all circuits that we deal with operate between 0 and VDD, which means that all our signals will nominally be at VDD by 2 and will jump up and down around VDD by 2. So, let me call that voltage VCM is the VDD by 2. So, this signal that we wish to sample will be of the form VCM plus say A sin omega t. All right. Now, when the switch is on, Vg must be connected to the, when you are tracking, the transistor must be on, right. So, when it is tracking, you want to make sure that the resistance of the switch is the smallest possible, so that you have a high tracking bandwidth. So, if you had a fixed transistor size, what you would do would be to connect the gate to the highest possible potential, and the highest possible potential that we can think of is VDD. So, VG must be connected to VDD during the track phase, and VG must be connected to ground during the hold phase. Does it make sense? Now, that means that Vg of t must look like this. This is VDD and this is 0, and this corresponds to track and this corresponds to hold. Now, let us see what non-idealities there are in this circuit. If everything works fine, we just move on, we are done, right. If things do not work properly, we need to see what the problems are and fix those problems. So, one thing that one should notice is that the MOS transistor's resistance depends on VGS minus VT. So, if you plot the waveform at the input, what does this waveform look like? It is simply a sinusoid hovering around. This is time, this is VCM, this is VCM plus A. Right. Now, can you comment on the gate source voltage of the transistor? So, the gate during the track, I mean of course, the gate potential is varying, right. During the track phase, can you comment on the gate source voltage? What is the gate source voltage? Vg, the gate voltage is simply VDD during the track phase. What about the source voltage? It is VCM plus whatever input there is. Let me call this A sin omega t. Correct? So, what is VGS? Pardon? During the track phase. During the track phase, what is happening is that, let me, since there seems to be some confusion, let me, during the track phase, the gate is connected to VDD, the input is connected as such, VCM plus A sin omega t, and the capacitor is here. So, if the switch resistance is chosen to be sufficiently small, which is what one would do in practice, then the drop across the transistor should be very small compared to the drop across the capacitor, correct. Okay. So, the source gate voltage or the gate source voltage of the transistor is nothing but VDD minus VCM plus A sin omega t, which is VDD by 2 minus A sin omega t. What do we notice? What do you think, is there a problem?
Time constant is a function of input.
Pardon?
Time constant is a function of input. Last time.
A function of input what?
Input amplitude. Amplitude.
Yeah. So, basically I mean one thing you notice is that the on resistance of the switch is proportional to or inversely proportional to VGS minus VT. As the input keeps changing, the gate potential is fixed in the track phase, but the source potential is varying. That is basically the input you want to sample. If the input becomes too high, what is happening to the gate source voltage? It is reducing, right. If the gate source voltage reduces, what happens to this quantity VGS minus VT? Reduces. If this reduces, what happens to the resistance of the switch? Increases, right. And on the other hand, when the input is the negative half of the cycle, the gate source voltage is increasing, which means that the RC time constant is decreasing. And one extreme case is what he pointed out, which is if the input voltage becomes too high, you stand the danger of turning off the transistor during some part of the cycle, correct, because if this potential becomes so high that this drop becomes less than Vt, then the transistor will be turned off. You understand? Okay. So, this is a problem because the resistance of the switch is now a function of input amplitude. So, is this a linear phenomenon or a non-linear phenomenon? It is a non-linear phenomenon, which means that it can result in what? It can result in harmonics, or it can result in distortion. You understand? So, let us try and understand in a more quantitative manner what happens. So, So, in general we see that this resistance is non-linear. Intuitively, let us try and quickly sketch what one must expect for the output to look like if the input was like this and the resistance of the switch was larger when the input went up and smaller when the input went down. What do you think you should expect? If the resistance becomes larger when the input goes up, what does it mean for the bandwidth of the RC network? Reduces. If the bandwidth reduces, what do you think will happen to the delay between the input sinusoid and the output sinusoid? The phase shift or the delay increases, whereas when the resistance decreases from the nominal value, the phase difference between the output sinusoid and the input sinusoid must reduce. So, what you can expect is some waveform this is a bad rendering, but I hope you get the idea. Okay. Yes. Well, I mean, I do not know about good or bad, but one thing you must make, I mean, this is clearly not a linear phenomenon, that is what I am trying to say. Okay. I mean, this is a grossly exaggerated picture for you to be able to see and understand, right, but this is what, this is the kind of waveform that you must expect. As you can see, the phase difference between the input and output is much higher for larger values of amplitude and smaller when the input goes into the negative half of the cycle. In general, you can kind of model in order to get an idea of what this does to the distortion. One can model the resistance of the switch to depend on the input voltage using a polynomial, right. So, in other words, let us say the resistance depends on the input voltage. So, let us say this is VCM plus A sin omega t. Under nominal conditions, when A is 0, the voltage drop across the switch, what do you think would be the voltage drop across the switch? Pardon? Yeah, we assume it is small, but when, let us see. So, if the voltage drop across the switch is very small, then what is the voltage drop across the capacitor approximately? It is roughly the input. So, the output voltage is approximately VCM plus A sin omega t, which means what is the current through the capacitor approximately? It is Ca omega cos omega t. This is the displacement current through the capacitor. Now, why is there a drop across the switch? There is a drop across the switch because the switch has got finite resistance and there is some current flowing through the switch, and the current flowing through the switch is approximately, this current is approximately Ca omega cos omega t. You understand? So, if the switch was perfectly linear, the resistance of the switch would be constant. In other words, the voltage drop across the switch would be what? Current through the switch is Ca omega cos omega t. The resistance of the switch, if it was constant, would be some R on. So, the voltage drop across the switch would be R on into Ca omega cos omega t. This is an approximate relationship, given that we have assumed that the voltage drop across the switch is small in relation to the amplitude of the voltage waveform across the capacitor. Does it make sense? You will get the same thing if you use Laplace transforms and use the approximation that omega is much smaller than 1 by RC. I mean, what does it mean physically to have a large tracking bandwidth? It means that the voltage drop across the switch is much smaller compared to the input, which means that the output amplitude will roughly be the same as the input amplitude. Is this clear? Right. Now, unfortunately, so this is what you would have for a linear switch. Now, unfortunately, the resistance of the switch is no longer linear and it depends on the input amplitude. So, let me say the resistance of the switch is of the form is a function of input amplitude and is of the form some R on, which is a constant, plus something which depends on A plus something which depends on A square and so on. All right. When it is non-linear, we know that, for instance, if the input amplitude is positive, or rather the input is positive, then let me not confuse you by calling this A, let me call this V in, so that, and if V in is chosen to be a sinusoid of amplitude A, then all these relationships hold. So, instead of calling this A, I will call the resistance of the switch, which is now dependent on V in. And why does this resistance being dependent on V in make sense? It is because the MOS resistance is being modulated by the input voltage. So, it is R on plus R 1 times V in plus R 2 times V in square plus higher order terms. Hopefully, the first two terms are good enough to modulate reasonably accurately, or at least for us to get an idea of what effect the nonlinearity of the switch has on the waveforms. So, if the resistance is expressed as in this form, do you think for the specific case we are talking about, do you think R 1 is positive or negative? So, if R 1, if V in increases, if V in is positive, the resistance increases. So, R 1 is positive. You understand? So, depending on the nature of the device, okay, we can go and evaluate what these R 1 and R 2 will be. You understand? In fact, for the MOS transistor, this is the resistance of the switch. VGS can be expressed in terms of
VDD minus
VDD, as VDD minus some VCM minus Vn and all this stuff. Vt is also dependent on VSB, which is VCM plus Vn, correct. So, both VGS and Vt depend on the input through some complicated expressions, but the bottom line is that the resistance depends on the input and can be modeled to a first order like this. Now, if this is the resistance, what do you think the drop will be across the resistance?
this the into current.
The voltage drop across the switch is simply current flowing through the switch times its resistance. The resistance now happens to depend on Vn, correct. So, and the current is what? The sampling capacitance dVn by dt times R on plus R1 times Vn plus R2 times Vn square. And this is an approximate relationship. Why is this an approximate relationship? Where is the approximation here?
Because while calculating current, we assumed that.
So there are this is an approximate relationship because we have used C dV in by dt to find the current through the capacitor, whereas the true current through the capacitor is what? The current through the capacitor is C dV out by dt, right. What we are saying is that if the drop across the switch is very small, then V out and V in are about the same, which means that the current to the capacitor can be approximated by C dV in by dt. Does it make sense? Now, if C dV in dt is the current and this is the resistance, the drop is simply the product of the two. Now, let us try and evaluate this for a special case of a sinusoidal input. So, if V in is say A sin omega t or omega in times t, then the voltage drop across the switch becomes C A omega in cos omega n times t times R on plus R 1 A sin omega n times t plus R 2 A square sin square omega n times t. Does it make sense? Right. And what is this? C A omega n times R on cos omega n times t plus C A square R 1 omega n times cos omega n times t times sin omega n times t plus C A cube R 2 omega n cos omega n times t times sin square omega n times t. Right. So, what do you think these terms are? So, one can replace 2 times cos omega n t sin omega n t, sorry, one can replace the product sin and cos by sin 2 omega n times t. And what about this character? 1 minus 2 sin square omega n times t is cos of 2 omega n times t. So, which means that this now can be replaced by 1 minus cos 2 omega n times t and this can be further simplified into C A cube R 2 omega n by 2 times cos omega n times t minus C A cube R 2 omega n by 4 times cos 3 omega n t plus cos omega n t. All right. Okay. Now, before we get some more intuition on this, one thing I would like to point out is that if you want to build a fairly decent sample and hold, can you comment on the various terms here, the relative magnitudes of R 1 V n and R 2 V n square versus R on? What are the dimensions of R 2? Ohm per volt square and R 1 ohm per volt. So, if you want to make a fairly decent sample and hold, in other words a fairly linear one, what will you try and attempt by design? You will try and make this term and this term much small compared to what? R on, right. So, in other words R on you would try and make it larger than, or you choose and try and make the switch such that R 1 V n and R 2 V n square, the drops associated with those terms, the nonlinear terms, is much smaller than the drop associated with the linear term, right. Now, therefore, if you kind of try and use that intuition here, the drop across the switch can be simplified to be C A omega n times R on cos omega n t, and what else? There are other terms which have cos omega n t. One is C A cube R 2 omega n by 2, and the other term corresponding to omega n is C A cube R 2 omega n by 4. So, by the discussion we just had regarding if you had a fairly linear switch to begin with, then these terms will be very small in relation to the term contributed by R on. So, you can kind of neglect those in comparison to the term contributed by R on. Does that make sense? Okay. So, this is, which means that we can now get rid of these two characters. We are left with the component at 2 omega n and 3 omega n, and they are
somewhere down the line you have to design such a way that they are not yet complete. That's the point. Because the first term remaining terms should be negligible.
I mean that is the idea, right. Eventually if you want to make a linear switch, you want to make sure that these R 1 and R 2 become, I mean see, when we are talking about the first macro model for the switch, we just assumed finite on resistance. The only problem that causes is tracking bandwidth, and thermal noise is of course a fundamental thing, there is nothing you can do about it, all right. However, now if the switch is nonlinear, in other words the resistance of the switch depends on the input, apart from tracking bandwidth issues, the drop across the switch also has components which are harmonics of the input frequency, right. So, this represents the drop across the switch. Let us try and stare at this expression and see if this makes, why this makes sense, all right. First, why do you think there is a term which is proportional to omega n? Why do you think that makes sense? The drop across the switch is proportional to the current is given by C dV dt, right. So, as the input frequency increases, the current through the capacitor increases, causing a larger current in the switch, therefore increasing the drop across the switch. Okay. Now, why does it make sense that the second harmonic current is proportional to the input amplitude square? Where is the second harmonic term coming from? It is coming from the V in square, and where is this V in square coming from? The second harmonic is coming from R1 V in multiplying with dV in dt, you understand. So, the second harmonic is coming because the current has a component A, the resistance is varying and the amount of variation also depends on A. So, the drop is this multiplied by that. So, that is why you get A square. Similarly, the third harmonic is coming from the R2 V square term, correct?
When you say harmonic, you mean 2 omega n.
Yes. What harmonic means frequency, yeah. No, I am saying the amplitude of the second harmonic is proportional to A square. Is this clear? Okay. And why it makes sense is because the second harmonic is coming from this component of the resistance multiplying with the current. As the input amplitude increases, this goes up by a factor of A, so does the change in the resistance. So, when you multiply the two, you get a second harmonic component which is proportional to A square. Similarly, the third harmonic component is proportional to AQ, and the way you would have designed the track and hold, you would have tried to make this, I mean this is a linear term, that is the voltage across the fixed part of the resistance, and that is a linear term, it does not cause harmonics. Okay. So, as we expect, because of the nonlinearity of the switch, there are harmonics, which is a characteristic of a nonlinear system. You put in a sinusoidal frequency of some omega n, and there are voltages and currents in the network which are at multiples of omega n. Does it make sense?